Imagine standing under a cold, moonless sky. No telescope, no flashlight, no notebook, just your breath in the frozen air, and your eyes scanning the endless dark above. The stars don't twinkle romantically. They burn, silently, indifferently, and you're expected to understand them, before telescopes changed everything. Astronomy was not a noble pursuit of cosmic wisdom. It was an exhausting, frustrating, and often terrifying job. The sky was your only textbook, and it never stayed still. You had no tools to help, no guidance beyond myths and flawed charts. Your nights were long, your calculations endless, your mistakes dangerous. In a world ruled by kings, priests, and superstition, guessing wrong about the heavens could cost you your career. Or worse, yes, astronomers were respected, but they were also used. They were pressured to predict eclipses, guide rituals, and shape destinies, while secretly battling confusion, exhaustion, and fear. There was no romance in this work, only isolation, guesswork, and the slow crawl toward truth. In this video, we'll take you deep into the world of ancient and medieval astronomy, before telescopes, before Newton, before modern science. You'll discover how early astronomers worked, what they feared, how they survived, and why their lives were far more painful than poetic. Stick around until the end. You'll never look at the night sky the same way again. This is Restless Historian, where we uncover the forgotten struggles behind familiar history. Subscribe now, and let's begin. Long ago, there were no telescopes, no computers, no charts or lenses. People had only one tool to study the sky. Their eyes. All observations were made with the naked eye. Nothing else. If someone wanted to know where the stars were, they had to look up. If they wanted to know when the moon would rise, they had to wait and watch. People watched the sky every night. They used their memory to track what they saw. They remembered when certain stars appeared. They noticed which ones disappeared. They followed the moon through its phases. They learned how the sky changed from night to night. But it wasn't easy. There were no streetlights, no cameras, and no second chances. If you missed something, you had to wait days, sometimes months, for it to happen again. The nights were often cold. There were no heaters, no warm buildings. Observers had to sit outside, in the wind, in the dark, in the silence. They wrapped themselves in whatever they had, blankets, furs, thick robes, and waited. Their eyes got tired. They blinked a lot. They rubbed their foreheads. They stared at the sky until their vision blurred. Sometimes they thought they saw something, but it was only a cloud, or their own breath in the cold air. But they kept watching, even in the freezing cold, even when nothing changed for hours. They kept watching. Why? Because the sky mattered. The stars were their calendar. The moon helped them count time. The sun marked the seasons. Without clocks or schedules, the sky was their only guide. Farming depended on it. So did travel. So did religious rituals. Kings made decisions based on the stars. People arranged their lives by what they saw above. But the work was slow. It took months, sometimes years, to notice patterns. And without instruments, mistakes were common. They often confused stars and planets. They thought the planets were stars that moved. Some stars blinked, others didn't. It was hard to tell what was real. When a bright object moved across the sky, it was called a wandering star. Today, we call it a planet. But back then, no one really knew what it was. And when something strange happened, like a solar eclipse, people were scared. The sun would vanish, the sky would darken, birds would go quiet, animals would act strangely. To the watchers, it seemed like magic, or a sign, or a punishment. They wrote down what they saw, but not everyone could write. Some used symbols, others carved shapes into stones. Some made small marks on bones or sticks. Every culture had its own way of recording. Some used clay tablets, some used bark or cloth. But always, it started with the eyes, watching, waiting, guessing. The sky was full of patterns, but those patterns were hard to follow. The stars moved slowly, but they moved. The moon changed shape. The sun shifted position on the horizon. Over time, people began to notice these things. They started to understand seasons. They knew when to plant, when to harvest, when the rains would come, when the snow would fall. All by looking up. They made star maps, not exact ones, just pictures, dots and lines, simple shapes in the sky. These shapes became constellations. They looked like animals, people, and objects. One looked like a hunter, another like a lion, others like fish, birds, or serpents. They gave these constellations names and told stories about them, legends, myths, tales passed down through generations. The constellations helped them remember. They acted as a guide. When you saw Orion, you knew winter was near. When you saw Scorpio, you knew summer was ending. But the watchers didn't always agree. One group might see a bear in the sky. Another might see a warrior. Different cultures had different stories, different stars, different meanings. Still, they all kept looking and learning. Sometimes the stars didn't act the way they expected. They would disappear, or new ones would appear. These guest stars were often recorded. Today we know them as supernova, but then they were a mystery. Some thought they were spirits, or signs from gods, or the souls of the dead. One bright streak in the sky, a comet, could cause panic. Wars started. Kings worried. Priests prayed. Nobody knew what it meant, but everyone believed it meant something. And the cold continued. The wind howled. The hours dragged. Eyes watered from the cold. Hands shook from fatigue. And yet the watchers stayed. They were careful, methodical, patient. They weren't called scientists yet, but that's what they were becoming with each night of observation. They learned a little more. They noticed the moon had a cycle, roughly 29 days. It changed shape gradually, from new to full, then back again. They noticed planets had loops. Sometimes they moved forward, sometimes backward. This strange movement confused them. We now call it retrograde motion. They didn't know why it happened, but they saw it happen. They tried to explain it. Some imagined the planets were fixed too, crystal spheres. Others thought the Earth was at the center. The sun, the moon, the stars, all revolved around it. It made sense to the eye, because that's what the eye saw. But the eye can be fooled. Still, the effort never stopped. Day after day, night after night, century after century. They looked at the same sky. They asked the same questions. They made the same mistakes. And slowly, they made progress. They started to mark time more precisely. They tracked eclipses. They predicted the return of comets. They aligned temples with the sun, built monuments that pointed to certain stars. They used the horizon, the stars, the moon. They built calendars, made rules, passed knowledge forward. But it all began the same way. Someone, somewhere, looked up with bare eyes, in the silence, in the cold, and started to wonder. In the ancient world, math was still young. People could count. They could add, subtract, even multiply. But geometry and trigonometry, that was where things got tricky. They didn't have calculators. They didn't have decimals. They didn't even use the number 0 for a long time. And yet, they tried. They needed math to understand the sky, to measure angles, to track the movement of stars, to figure out where the sun would rise and when the moon would appear. But their math had limits, and those limits caused problems. It started with distance. People wanted to know how far away the moon was, or how big the sun might be. They guessed, of course, but they also tried to measure. One method was to use shadows. Stick a pole in the ground. Watch where the shadow falls. Measure the angle. It sounds simple, but it's not. A small mistake in the angle, just one tiny error, would throw off the entire calculation by hundreds, even thousands, of kilometers. Small errors, huge consequences. Still, they kept going. The Babylonians were among the first to try. They lived in Mesopotamia thousands of years ago. They loved numbers, especially base 60 numbers. That's why we still use 60 seconds in a minute, and 360 degrees in a circle. They watched the sky carefully. They tracked planets. They recorded eclipses. And they built tables. Not wooden tables, math tables. Lists of numbers, predictions, of when things would happen in the sky. But their math was mostly arithmetic. They didn't have full geometry, so they could describe what they saw, but not fully explain it. Then came the Greeks. The Greeks were obsessed with shapes, circles, triangles, lines. They believed the sky moved in perfect circles, because circles seemed pure, flawless. They also developed early trigonometry. They used right triangles, ratios, angles. They started to ask new questions. What angle does the sun make at noon? How long is the shadow at sunrise? How high is the moon above the horizon? They wanted to know how the heavens worked. They imagined spheres spinning in the sky. Each planet was fixed to a crystal sphere, all of them turning in perfect harmony. They created complex models. Some worked well, others didn't, but they believed in math. They believed math could describe the universe, and they weren't wrong. But their math was not yet accurate enough. They made lots of assumptions. One wrong assumption could ruin the whole system. For example, they believed the Earth stood still, that everything in the sky revolved around it. It looked that way. So they assumed it was true. They built their math around this idea, and that created problems. To explain why planets seemed to go backward, they invented loops. They said planets moved in tiny circles, while also moving in big circles around Earth. These tiny circles were called epicycles, and the math behind them was complicated. Very complicated. It worked, sort of. It could predict where planets would appear, but it was full of patches, fixes on top of fixes. One correction here, another correction there. The models looked elegant on paper, but in practice, they were a mess. Still, it was the best they had. Then came the Arabs. During the Islamic Golden Age, scholars across the Middle East picked up where the Greeks left off. They translated Greek texts. They studied geometry. They advanced trigonometry. They improved star charts. They even built observatories. They created tools to measure angles in the sky. They called them astrolabes, and quadrants. With better instruments, they got better numbers. But even small errors in angle, just 1 degree off, could ruin an entire night's work. They tried to calculate the size of Earth. Some got close. Others didn't. They tried to measure the distance to the moon and the height of stars above the horizon. Again, small errors. Big mistakes. Even measuring time was hard. They didn't have precise clocks, only sundials and water clocks. But sundials only worked in sunlight, and water clocks weren't very accurate. So when did a star rise? How long did an eclipse last? What time was it exactly when the moon turned red? Hard to say. Observers had to guess, write things down, hope their memory was right. Over time, the math improved. Tables became more accurate. Angles became better measured. Predictions became more reliable. But even then, a single mistake in copying numbers could throw off a whole century of data. One wrong digit, one smudged mark, one forgotten line in a scroll, and the next observer would get the wrong result. He'd base his entire study on flawed numbers, and he wouldn't even know it, so the curse continued. The wrong math kept causing trouble. Some believed planets moved in figure eights. Some believed the sun got closer and farther at random. Others believed the stars never changed, all because the math didn't match the sky. And it wasn't just astronomy. The same bad math affected navigation. If your star chart was wrong, you could end up sailing hundreds of miles off course. Sailors depended on accurate angles. They used the sun and stars to find their way. But if your angle was even a little off, you might miss an entire island. The wrong math could mean getting lost at sea, or crashing on rocks, or never arriving at all. Even building calendars was hard. Religious holidays, planting seasons, royal events, all depended on knowing the sky. But if your math was wrong, your calendar would drift. New Year might fall in summer. Harvest festivals could happen in spring. Eclipses could be predicted on the wrong day. And people noticed. They started asking questions. Why are the stars not where we said they'd be? Why did the moon arrive early? Why did our model fail? The math was to blame, but fixing it wasn't easy, because to fix the math, you had to fix the assumptions. And no one wanted to challenge old beliefs. The Earth in the center, that was tradition. Circles in the sky, that was philosophy. The idea that the heavens were perfect, that was sacred to fix the math. You had to let go of those ideas, and that took courage. For now, though, the errors remained. People kept watching the sky. They kept measuring. They kept drawing charts. And they kept struggling. Not because they were foolish, but because the tools were limited. The knowledge was incomplete, and the math was still not quite right. Long ago, looking at the stars wasn't just a hobby. It was a job, a serious one. Sometimes a dangerous one. In ancient courts, kings and emperors demanded answers. They wanted to know the future. They wanted signs from the heavens. They believed the sky held secrets, and they wanted those secrets revealed. That's where astrologers came in. They were more than star watchers. They were advisors for scientists, and sometimes scapegoats. If the king asked, "Will there be an eclipse next month?" you had to answer. If he asked, "Is this a good day to go to war?" you had to tell him. And if you were wrong, that could cost you everything, sometimes. It meant losing your job. Sometimes it meant public shame. And sometimes it meant death. The pressure was real and constant. Imagine standing in front of a ruler, a man with armies, a man who sees himself as chosen by the gods, and you, a scholar with scrolls and charts, have to tell him something he doesn't want to hear. If an eclipse was coming, he'd want to know what it meant. Was it a warning? Was it a sign of defeat? Was it the death of a rival? You had to give him an answer, not just the date, not just the time, but the meaning. People didn't just observe the sky, they interpreted it. They believed the stars told stories, that planets carried emotion, that comets screamed omens, and eclipses. Eclipses were terrifying to them. An eclipse wasn't just a natural event, it was cosmic drama, a clash of gods, a sign that the heavens were angry. When the sun disappeared during the day, people panicked, birds stopped singing, dogs howled, people dropped to their knees, crying, praying, begging, and the king, he turned to his astrologers. What does this mean for me? He'd ask if they gave the wrong answer, or if the event wasn't predicted in advance. They were in trouble. In China, imperial astronomers were expected to predict eclipses, down to the exact day. If they failed, they could be punished. 1. Record tells of astronomers being executed for missing an eclipse. It sounds extreme, but to the emperor, the sky was political. It showed his power. It reflected his fate. A surprise eclipse. That meant his astrologers weren't in control. And if they weren't in control, maybe he wasn't either. In Babylon, kings demanded daily reports from the sky. Astrologers had to track every movement, every glow, every shadow. They used clay tablets to record omens. If Venus appears in the west, this will happen. If the moon is dark on the 15th, expect trouble. It was part science, part superstition. In ancient India, eclipse predictions were tied to legends. People believed a demon swallowed the sun. The astronomers knew more. They could track the lunar nodes, points where the sun and moon crossed paths. Still, their predictions had to match the myths. They had to explain science without breaking belief. It was a balancing act. The astronomers were caught between two worlds, one of numbers and one of fear. They saw the stars as patterns, but the people saw them as prophecies. So, even when an eclipse could be predicted, it still had to be explained. Carefully, in the Islamic world, court astronomers rose to great heights. They built observatories. They charted the sky with precision. They corrected ancient errors. But even they faced pressure. The caliphs wanted predictions. They wanted proof that their rule aligned with the stars. They wanted reassurance that they had divine favor. The astronomers had to deliver. And what if they didn't? Their reputation could collapse. They could lose funding. They could lose their place at court sometimes. Religious scholars questioned their work. They asked, is this knowledge holy, or is it forbidden? Some said predicting the sky was a gift, a way to understand God's creation. Others said it was arrogance, trying to control what only heaven should know. So the astronomers had to walk carefully, speak gently, frame their work not as power, but as service. We don't control the stars, they'd say. We only observe them. We only measure what God has made. But the line was thin. Too much prediction, and they were accused of sorcery. Too little prediction, and they were seen as useless. In Europe, it was no easier. During the Middle Ages, astronomers had to follow church teachings. They could study the stars, but not question the structure of the heavens, not question the Earth's place in the universe. If their work challenged scripture, they risked censure, or worse. Still, kings demanded signs. Battles were timed based on astrology. Marriages were arranged by the stars. Coronations, crusades, deaths, all were tied to predictions. A well-timed eclipse prediction could bring fame, respect, royal favor. A wrong one could end it all. Some astronomers learned to give vague answers, like fortune tellers today. Something unusual will happen. A change is coming. Beware the East. This kept them safe, but it slowed progress. Science needs risk. It needs bold claims, precise numbers, clear results. But when your life is on the line, safe guesses feel smarter. This constant fear held back discovery. Many astronomers had brilliant ideas, but kept them hidden, wrote them in code, whispered them in private. They feared what would happen if their ideas were misunderstood, and often they were. A prediction might be made for the sake of learning, but taken as a threat. A mistake might be seen as a lie, or a betrayal, so they tread lightly. They still looked up, still measured, still charted stars and phases, but always with caution, always with eyes over their shoulders. Some worked in secret. Some fled their countries. Others gave up altogether, and yet some stayed. Some pushed forward, because for them, the stars meant more than fear. They meant knowledge, order, truth. They believed the sky could be understood, that the universe followed rules, that behind the omens and the myths there were numbers, equations, patterns. But to find those patterns, they had to survive the pressure. They had to balance curiosity with caution, science with politics, truth with tradition. It wasn't just about the sky, it was about power, and the people who demanded answers from it. So every night, when they looked up, they weren't just seeing stars. They were seeing deadlines, decisions, demands, and with every eclipse, every shadow, every flicker of a planet, they knew they had to get it right. In the 2nd century AD, a man named Claudius Ptolemy sat down in the Egyptian city of Alexandria and tried to explain the universe. What he created would shape the way people saw the cosmos for over 1,400 years. His book was called The Almagest. It was big, complex, detailed, and for centuries, it was the final word on astronomy. At the heart of Ptolemy's model was one simple idea. The Earth is at the center of everything, the sun, the moon, the stars, the planets, all of them revolved around us. Today we know that's not true, but back then it made perfect sense. When people looked at the sky, it looked like everything moved around the Earth. The sun rose in the east. It set in the west. The stars circled above like a great dome. The Earth didn't seem to move at all. So Ptolemy took that idea and built a system around it. It was brilliant. It was wrong, but it was brilliant. He created a detailed mathematical model of the heavens. He used circles, lots of them, to explain how planets moved in strange loops across the sky. He invented a system of epicycles, tiny circles riding on bigger circles. It was complicated, but it worked. It made predictions. You could use it to say where a planet would be in the sky tomorrow, or next year, or decades later. That was powerful, and because it worked, people trusted it. Ptolemy's model wasn't just popular, it became untouchable. For generation after generation, his ideas were taught as fact, copied into books, translated across languages, used in schools, used in churches, used in royal courts. It wasn't just a theory, it was truth, questioning it. That wasn't just foolish. It was dangerous to say the Earth might move, or that the sun might be at the center instead. That could get you labeled a heretic, because Ptolemy's model fit more than just science. It fit with philosophy and with religion. In the Christian world, people believed Earth was special, the center of God's creation, made first, made for humans. If Earth wasn't in the middle, what did that say about us? So when Ptolemy's system came along, it fit perfectly with that worldview. It wasn't just science anymore. It was sacred. The model was so deeply woven into culture that challenging it was like pulling a thread from the whole fabric. It threatened everything. That's what made it a trap. Because even though the model wasn't perfect, people stuck with it, even as new observations came in, even when the math got more and more messy. They kept patching the system, adding more circles, more loops, more explanations. Instead of starting fresh, they added more layers. Imagine building a house on sand, and every time it sinks, you just add another floor. That was the Ptolemaic model. Still, you can't blame them. By the standards of the time, Ptolemy was correct. He wasn't guessing. He was using data. He was using math. He was solving real problems. And most of the time, his predictions actually worked. The sun came up when it was supposed to. The planets were where the charts said they'd be. Eclipses could be predicted. Seasons could be tracked. So if the model gave the right answers, why question it? That's why it lasted. But underneath, the problems were piling up. For one, the motions of the planets didn't quite fit. Sometimes they moved faster, sometimes slower. Sometimes they looped backwards, what we call retrograde motion. To explain this, Ptolemy used more epicycles, and then equidistant, and other clever tricks. With every new issue, he added another fix. And for a while, it worked. But slowly, cracks began to show. Over time, astronomers started to see that the model was too complex, too forced, too full of patches. Some quietly wondered, what if the Earth wasn't at the center? What if that was the root of the problem? But saying that out loud, that was risky. Even brilliant thinkers were afraid. If you were wrong, you'd be mocked. If you were right, you could be punished. Many scientists believed the Earth moved, but only whispered about it, because to challenge Ptolemy was to challenge the worldview of kings, priests, and scholars alike. And yet, the idea wouldn't go away. Some people noticed that the math got easier when you placed the sun in the center, that the planets made more sense, that their speeds matched better, that the retrograde motion disappeared. But these ideas stayed hidden for centuries, because Ptolemy wasn't just a scientist, he was a symbol, and his model wasn't just a theory, it was a cage. Even in the Islamic Golden Age, where science flourished, many scholars still followed the Ptolemaic system. They improved it, refined it, added better tables and tools, but they still held on to the central idea. Earth in the middle. Always. It wasn't until the 1500s that a new idea began to break through. A quiet, careful astronomer in Poland, Nicolaus Copernicus, started to rethink everything. He wasn't the first to suggest the sun was at the center, but he was the one who made it stick. Still, even Copernicus was cautious. He delayed publishing his book. He dedicated it to the Pope, hoping for protection, and he framed his model as just a mathematical tool, not a literal truth, because the Ptolemaic trap was still strong. It wasn't just about being right, it was about being accepted. It took even more time, and people like Galileo, Kepler, and Newton to finally break free from the model. Galileo used a telescope, a new invention at the time, to show the phases of Venus, proof that the planets went around the sun. But he faced trial, house arrest, condemnation, because the old model still ruled minds. The trap wasn't just in the science, it was in the culture, the politics, the pride. For over 1,000 years, the Ptolemaic model was considered untouchable, and anything else dangerous, laughable, blasphemous. That's why it lasted so long. It was a mix of habit, belief, and fear. People didn't want to be wrong. They didn't want to rewrite the books. They didn't want to admit that the sky worked differently than they thought, so they stayed in the trap. And yet, they kept looking up, kept measuring, kept wondering, and slowly, piece by piece, the truth began to break through. In the ancient and medieval world, stargazing wasn't just about looking up. It was about measuring, tracking, trying to bring order to the sky. But back then, there were no telescopes, no cameras, no digital anything, just metal, wood, and imagination. So people built tools, big ones, complex ones, beautiful ones. But here's the truth. Many of those instruments, they barely helped. They looked impressive. They felt important. They were hard to use, but they often didn't fix the core problems of ancient astronomy. Let's start with one of the most iconic tools, the armillary sphere. It's a metal model of the sky, rings within rings, a globe of circles. It shows the equator, the celestial poles, the path of the sun, called the ecliptic. You could rotate it, align it with the heavens, visualize how the stars moved. It was beautiful, elegant, but not very practical. The armillary sphere didn't tell you anything new. It didn't make your measurements more accurate. It didn't help you see stars that were too dim. It just helped. You imagine how the sky worked. In that way, it was more symbolic than scientific. You could use it to explain ideas, to teach students, to impress nobles. But in the cold dark of night, when real observation was needed, it was often left behind. Then, there was the a flat disk filled with numbers and symbols, rotating plates on a frame, a mix of math and art. It could tell you the time. It could help you find the altitude of a star. You could use it for navigation, prayer times, or astrology. It was versatile, but it wasn't simple to use it well. You had to understand spherical geometry. You had to know the coordinates of stars. You had to read the sky with extreme precision. A small mistake with your hand, or a shift in the atmosphere, and your whole calculation was off. And still, even with a perfectly used astrolabe, you were limited by your eyes. You could only observe what you could see, and you could only measure what you could align perfectly, in the dark, with no lights, no magnification, no backup. The quadrant was another favorite. It was shaped like a quarter circle, sometimes made of wood, sometimes brass. It had a sight on one side, and a plumb line for measuring angles. You could hold it up to the sky and measure the angle between a star and the horizon. That gave you the star's altitude, and from that you could guess your latitude. Again, clever idea, but tricky to use. You needed a steady hand, a clear view, a calm night, and even then, the quadrant was usually limited to one measurement at a time. No continuous tracking, no real-time accuracy, just one angle, written down and hoped for the best. There were larger versions too, wall-mounted quadrants in observatories, giant versions used by Islamic astronomers, Chinese scholars, and European monks. But size didn't solve everything. The same issues remained: human error, weather, eyesight, and shaky math. One wrong tilt, and the numbers were meaningless. The sextant came later, and was more precise, especially at sea. But even it relied on skill and perfect timing. And for astronomers trying to predict eclipses, track planets, or map the heavens, it still wasn't enough. Many of these tools had one big flaw: they couldn't solve the core visibility problem. The night sky is full of obstacles: clouds, haze, moisture in the air, light from the moon, dust near the horizon. Stars twinkle because the atmosphere bends light. And the lower the star is in the sky, the more it dances, distorts, and dims. No instrument could fix that. Not back then. You couldn't just zoom in on a star. You had to wait for it to rise higher, or hope for a better night. So even with tools in hand, astronomers often had to rely on memory and guesswork. Worse still, many instruments required perfect alignment. They had to face true north, they had to be level. They had to be calibrated, something hard to do in the dark, with no precise clocks, no GPS, no electricity. Some observatories built permanent tools, giant armillary spheres set in stone, or carved markings on walls. These were more stable, more reliable, but even then, errors crept in. Temperature changes made metal expand or contract. Wood warped, ropes stretched, hands slipped. And let's not forget, most of these instruments didn't just measure, they represented. They were symbols of knowledge, of wisdom, of power. In many royal courts, owning an astrolabe showed status. Displaying an armillary sphere on your desk meant you were educated, even if you didn't know how to use it. Scholars painted with these tools in their portraits. Kings gave them as gifts. They were items of culture as much as science. Some were made just for show, perfectly polished, engraved with gold, never meant to be used. Others were real tools, but used more for theory than practice. You might spend months building one, but only use it once or twice, because it didn't really make things easier, just more impressive. That's the strange truth. The ancient world was full of clever tools, but few of them made astronomy accurate. The real problem was the limits of the human body. No matter how good the instrument was, you still had to see with your eye, judge with your hand, record by candlelight, and calculate without calculators. Many tools depended entirely on skill. If you weren't trained, they were useless. If your hand shook, your data was ruined. Even today, if you try using a replica you'll see how tricky it is. Try lining up a star through a tiny hole, holding the disk level, reading off numbers in the dark. It's not easy, so while the tools were clever, they weren't miracles. They didn't solve the core problem. The sky is vast, and we are small, and without magnification, without clear optics. Most tools just helped people guess slightly better. They didn't reveal the universe. They just made the old problems look a little more elegant. Still, these instruments mattered, because they showed something else. The hunger to understand. Even if the tools were flawed, people still built them, improved them, passed them down. They didn't give up. Each awkward instrument was a step forward, a lesson learned, a seed planted for future science. And eventually, those seeds would grow into telescopes, into lenses, into real precision. But at the time, these early astronomers were stuck with metal circles and wooden arms. relying on their minds more than their machines, guessing, measuring, trying, night after night. For most of human history, looking at the stars wasn't just about science. It was about faith, about gods, heavens, and divine order. Every culture had its own sky stories. The stars weren't just dots of light. They were signs, messages, clues from above. Astronomy, as we think of it today, didn't really exist yet. It was celestial religion, a sacred art. Priests tracked the stars. Temples aligned with the sun. Monuments were built to mark solstices, eclipses, and equinoxes in Egypt. The rising of Sirius predicted the flooding of the Nile. In Mesoamerica, the Maya built pyramids that acted like solar calendars. In Mesopotamia, priests watched the skies for omens and portents. It wasn't about understanding how the universe worked. It was about knowing what the gods wanted. Curiosity was, there is, but it had to bow before belief. If you discovered something that didn't fit the accepted story, you didn't publish it. You didn't share it. You buried it, because, in many times and places, the wrong idea could get you labeled a heretic. In the Islamic world, during the Golden Age, scholars made huge advancements in astronomy. They built observatories, mapped stars, refined tools, translated Greek texts, and expanded on them. But even they had to walk carefully. The Quran placed Earth in a special role. Many believed the universe had a divine order that shouldn't be questioned. So, if an astronomer came up with a theory that contradicted that order, he risked backlash. Sometimes, discoveries were hidden in the form of hypotheses, just models, they would say, not the truth, just ways to help calculate, not to challenge God. In Europe, the church held a firm grip on knowledge. The Bible said the earth didn't move, that it was fixed, that the sun and stars moved around it, and for centuries, that belief shaped science. Ptolemy's earth-centered model fit this worldview perfectly, so it became sacred science, approved, defended. Anyone who said otherwise risked everything. Some thinkers had doubts, some saw flaws, some believed the sun might be the center, but they kept silent, or they wrote in secret, or they framed their ideas as mathematical tricks, not reality, because religion was the authority, and challenging that authority meant trouble. When Copernicus published his sun-centered model in the 1500s, he was cautious. He delayed for years. He made sure to dedicate the book to the Pope, and even then, he presented it as a convenient model, not a literal truth. That's how sensitive the subject was. After him came Giordano Bruno. He took it a step further. He said the universe was infinite, that stars were other suns, that Earth was just one of many worlds. For that, he was burned at the stake, not for astronomy alone, but for ideas that clashed with church teachings. Astronomy wasn't just science anymore. It was a battlefield. Even Galileo knew the risks. When he turned his telescope to the sky, he saw things no one had seen before. Mountains on the moon, moons orbiting Jupiter, phases of Venus. Evidence that Earth was not the center. Evidence that challenged church doctrine. He published his findings. He argued for the sun-centered model. At first he had support, even from some within the church, but the pressure grew. Eventually, he was tried by the Inquisition, forced to recant, placed under house arrest, all for looking up and sharing what he saw. That's how dangerous curiosity could be. It wasn't just about facts. It was about power, Religious institutions feared what new knowledge could mean. If the earth wasn't at the center, did that make humans less special? Did it undermine scripture? Did it shake the foundations of belief? Many thought. So astronomers had to choose their words carefully. They used coded language. They wrote for private use. They waited until after death to publish. In some cases, their works were banned, their names erased, their books burned, and yet they kept going, because curiosity doesn't stop, even under threat. Some scientists tried to blend their findings with faith. They would say, yes, the sun is at the center, but it's part of God's greater design. Yes, the stars are far away, but they were placed there by divine will. It was a balancing act. 1 foot in science, 1 foot in religion. But not everyone could keep that balance. In many cultures, astronomy and astrology were one and the same. The stars didn't just move, they influenced life. Kings had court astrologers. They wanted predictions, signs, warnings. Astronomers were often expected to deliver cosmic messages that made their role political and risky. If they got it right, they were praised. If they got it wrong, they were punished. And if they discovered something that didn't fit the king's worldview, they kept it to themselves, even in places where science was respected. It had limits. In China, astronomers worked for the imperial court. They kept calendars, predicted eclipses, helped maintain harmony between heaven and earth. But they were watched, controlled, and not always free to question, because their role wasn't just scientific, it was ritual. The stars were part of the social order, and messing with that order was dangerous, so over and over again. Curiosity had to fight for space, not against ignorance, but against belief, not against the unknown, but against the fear of what truth might mean. Some discoveries were forgotten because they were too inconvenient. Some ideas were centuries ahead of their time, but ignored. Others were distorted to fit what people already believed. The shape of the cosmos, bent under the weight of human fear. Still, some astronomers found ways to hide in plain sight. They wrote in riddles, in metaphors, in complex diagrams no one but other scientists could understand. Knowledge moved underground, passed in secret, shared only with trusted minds. It was a kind of quiet rebellion, because for them, the sky wasn't just a reflection of divine power. It was a puzzle, a mystery, a challenge, something to be solved, not worshipped. And even with danger all around, they kept asking questions. Why do planets move the way they do? Why does the moon change shape? What causes eclipses? How far are the stars? Simple questions, but at the time, dangerous ones, because behind each question was a hint. Maybe the universe doesn't revolve around us, and that idea, more than any observation, was the real threat. It shifted perspective. It moved humans off the throne. It opened the door to new ways of thinking. That's what made curiosity so powerful, and so dangerous. And in the end, even religion couldn't hold it back forever. But in those early centuries, when science and faith were tangled together, every new discovery came with a cost. The sky was full of secrets, but not everyone was free to speak them. Imagine trying to study the sky without a watch, without a clock, without time zones, without even a calendar you could fully trust. That was reality for most early astronomers. There was no standard time, no shared system. Every village, city, or kingdom ran on its own version of what time it thought it was, and that made studying the stars incredibly frustrating. Time is everything in astronomy. You need to know exactly when something happened, what hour, what minute, even what second in some cases, because the stars move, the planets shift, the sky is always in motion. So when someone in one city wrote in their logbook, Jupiter appeared just after midnight, it meant almost nothing to someone reading it in another town. Whose midnight? What calendar? What counting system? Was it a lunar calendar? Solar? A king's reign year? Did their days start at sunset or sunrise? Without standard time, the entire sky became a moving target. Even if two astronomers looked at the same planet, they often wrote down different times, different coordinates, and different interpretations. This wasn't because they were bad at their jobs. It was because time itself wasn't fixed. Mechanical clocks didn't really become reliable until the 14th century, and even then, they were rare. Early clocks were made with gears and weights, and they lost time constantly. Some were off by several minutes a day, and if your clock was off, your data was, too. Before clocks, time was often measured with sundials, hourglasses, or just human observation. People watched the sun rise and set. They marked the length of shadows. They burned candles or incense that lasted a known amount of time, but that only worked on clear days, or in specific seasons, and it still wasn't precise. So astronomers often relied on their best guess. They would estimate based on the position of the moon or the stars they could see overhead. But even then, timing was rough at best. Let's say someone in Babylon wanted to track a lunar eclipse. They saw the moon darken at what they thought was the second hour of the night. They recorded it. They passed it down. It became part of the historical record. But hundreds of miles away, another astronomer saw the same eclipse an hour earlier, according to their system. Which one was correct? It's impossible to know for sure. Without a shared reference, even simple observations became messy. Add to that the issue of location. When you look at the stars, your position on Earth changes what you see. Latitude and longitude matter. Some stars never rise in the north, some never set in the south. Planets appear at different times depending on where you are. So, a star chart made in Egypt might look completely wrong in India. An eclipse visible in Persia might be invisible in Greece. And if you didn't note your location carefully, your observations became meaningless to others. Now layer on the seasons. The Earth moves around the sun. That means the stars shift gradually, night by night. What's overhead in January isn't what you see in July. But many early cultures didn't fully grasp this movement. They knew the stars changed with the seasons, but they didn't always understand why. They just called them winter stars or summer stars. They grouped them by agricultural cycles. Plant when this star rises, they'd say. Harvest when that one fades. These systems worked sort of, but they weren't precise. And they didn't account for the gradual drift of the stars over time. Because here's another twist. The sky itself changes very, very slowly, but it does. There's something called the precession of the equinoxes. It's a wobble in the Earth's rotation, and it shifts the position of stars over centuries. It's subtle, about 1 degree every 72 years. But over time, it adds up. So a star that once rose exactly at the spring equinox might no longer do so. 500 years later, ancient astronomers had no idea why this was happening. Their old star maps started to feel off. Constellations didn't match up the way they used to, and without precise timekeeping, They couldn't track these long-term changes accurately. Some thought the heavens themselves were changing. Others blamed human error. But in reality, it was the Earth quietly tilting, slowly shifting, and nobody could measure it clearly because they had no fixed frame of reference. Even the calendar was unreliable. Many societies used lunar calendars, which don't match up with the solar year. Over time, the months drifted out of sync with the seasons. Others tried to fix this by adding leap months or switching to solar calendars. But every calendar reform caused more confusion. Different cultures used different year counts. Some counted from the founding of a city, others from the reign of a king, still others from a religious event. So two astronomers might be writing in the same year, but be decades apart by modern reckoning. This made comparing observations incredibly hard. You had to translate not just the language, but the entire system of time behind it. And when you finally lined things up, you still had to ask, did they observe at dawn? At nightfall, how did they define hours? Were they using a water clock, a candle, the shadow of a stick? Even within the same culture, time varied. In one city, the hour might start at sunset. In another, it started at sunrise. Some places divided the day into 12 daylight hours and 12 night hours. But that meant the length of an hour changed with the seasons. A winter hour was shorter than a summer one. So when someone said, "I saw Mars at the third hour," you had to ask, third hour of what kind of day? It was chaos, organized chaos, perhaps, but chaos nonetheless. And this chaos affected everything. Star catalogs became messy and inconsistent. Planetary tables didn't match across cultures. Eclipse predictions varied widely depending on who made them and when. Many early astronomers did amazing work. They built detailed models. They tried to unify time and sky, but without accurate timekeeping, their data was often flawed. Sometimes, a single wrong estimate in timing led to a completely wrong model of the heavens. A planet that seemed to jump in the sky might not be jumping at all. The observer just got the time wrong. Even today, historians struggle with these old records. They try to decode ancient logs, to match events to modern calendars, to figure out when and where things really happened. And it's hard work, because the sky never stood still, and time never stayed put. So before the age of mechanical clocks, and well before standardized time zones, every night was a guessing game. And even the most careful astronomers, the ones who stared at the stars for decades, were still at the mercy of a ticking clock that didn't exist. Studying the sky sounds peaceful, even poetic. But for early astronomers, it was anything but. It meant long nights, cold air, little sleep, endless waiting. There were no telescopes at first, no heated domes, no assistants bringing coffee or checking data. Just a person, a notebook, and the sky. Observing had to happen at night. That was the rule. That was the job. When the rest of the world slept, astronomers were wide awake, eyes fixed upward, fingers numb, breath visible in the air. The best stargazing hours were often the coldest. The sky cleared up after midnight. Moisture settled. Wind died down, but that also meant freezing temperatures, especially in winter, especially in mountains or open fields where the view was best. Some astronomers wore multiple layers: wool, fur, anything they could find. Others lit small fires to stay warm, but fire made light, and light ruined dark vision, so they had to choose warmth or clarity. Food wasn't a priority. Most brought bread, dried meat, maybe soup in a container, cold by midnight. There were no breaks for warm meals. You couldn't go inside. You'd miss the moment, miss the alignment, miss the one shot at capturing a rare event. So they sat there, silent, waiting sometimes for hours, waiting for a planet to rise, waiting for a star to transit, waiting for a shadow to appear on the moon. It wasn't fast work. It was repetitive, slow, often painfully so. You couldn't rush the sky. You just had to follow it, night after night, week after week, month after month. You recorded star positions, measured angles, checked the moon's shape, marked the times, compared notes from the night before. Then you checked it all again, and again, and again, because if you got it wrong even slightly, your whole theory could collapse. That kind of focus takes a toll, not just on the body, but on the mind. Astronomers lived strange lives. They slept during the day, stayed up all night, barely saw family, barely spoke to others. Some lived far from cities, to escape light, to escape noise, to find the perfect spot where the stars were brightest. But that meant isolation. Imagine sitting on a hilltop, all alone every night. Just you and the stars. No one to talk to. No one to help. Just scribbled charts, ink-stained fingers, frozen toes, and the occasional howl of a wolf or hoot of an owl. Some built small observatories, wooden shelters, rooftop platforms, stone towers. These places became their homes, not comfortable ones, just functional. Some were damp, leaky, cramped, and always cold, and yet they kept coming back, because the work had to be done, because the stars wouldn't wait, because no one else would do it. But not everyone lasted. The toll was high. Sleep deprivation was common. So were headaches, eye strain, back pain from bending over charts, stiff necks from staring up for hours. Some developed nervous tics. Some went blind in one eye. Others simply burned out. There were no vacations, no breaks in the schedule. If you missed one night, you might have to wait a full year for that same alignment to happen again. So people pushed through, even when exhausted, even when sick, even when everything in their body told them to stop. Mental health suffered. Imagine weeks of cloudy skies, no observations, no progress, just waiting. Imagine being halfway through an observation, when clouds roll in, everything ruined. You sit there, soaked in frustration, knowing you'll have to try again tomorrow, or the next week, or never, if the event was a rare one. There was a deep sense of loneliness in the work, not just physical isolation, but emotional distance. Most people didn't understand what astronomers were doing. They thought it was superstition, or madness, or wasteful, so astronomers kept to themselves, talked mostly to other astronomers, if any lived nearby. Some wrote letters to distant colleagues, sharing data, asking questions, comparing results, but even that was slow. Mail could take weeks, or never arrive at all. So for the most part, they worked alone. They built their own instruments, calculated by hand, mapped the heavens with nothing more than rulers, pens, and patience. And they questioned themselves constantly. Was that really Saturn? Did that star move? Was that a glitch in the lens, or a sign from heaven? Doubt crept in easily, fatigue made it worse, mistakes happened, and yet they continued. Some nights there was a kind of beauty to it, the silence, the rhythm, the feeling of being the only one awake, watching the universe spin. But those nights were rare. Most were a test of endurance, of focus, of will. And when dawn came, there was no celebration, no crowd, no applause, just pages of notes, sometimes illegible, sometimes brilliant, and a tired body that needed sleep, if only for a few hours before it all began again. Even those with passion sometimes broke. They started skipping nights, stopped recording details, made careless errors. Some gave up astronomy altogether. Others became obsessed, compelled to find patterns, to chase comets, to prove theories no one else believed. They spent their days buried in numbers, and their nights staring at points of light. Many died without recognition, their discoveries stolen, or lost, or misunderstood. Some left behind piles of notebooks no one would read, but some, a small few, made breakthroughs, because behind all the suffering, behind the cold and the isolation, was a question bigger than the pain. What is out there? And to answer that, they gave up comfort, they gave up sleep, they gave up everything, all for one more night under the stars. Back then, there wasn't a clear line between astronomy and astrology. In fact, there was almost no line at all to study. The stars was to predict what they meant. Where planets moved, fate followed. What the moon did mattered. If Mars rose early, it wasn't just a planet. It was a sign of war, of anger, of something big about to happen. In many ancient societies, the stars weren't just part of science. They were part of destiny. So if you wanted to study astronomy, you almost always had to work as an astrologer too. There was no choice. That was the only way to get paid, to get respect, to get access to the tools, libraries, scrolls, and time needed to do real work. No king or noble would fund a skywatcher just for curiosity. They wanted results, predictions, horoscopes. When would I fall ill? Will this child become king? Is today a lucky day for battle? And the astronomer, even if he hated it, had to answer, because if he didn't, someone else would. This was the bargain many astronomers made. They fed the beliefs of the rich, just so they could sneak in some real science on the side. They mapped stars between writing horoscopes. They tracked planetary motion while pretending to read omens. They watched eclipses in secret, then claimed it was all part of a divine pattern. Most didn't believe in astrology, not fully. They knew that stars didn't control people's thoughts, that a comet wasn't a curse, that a planetary alignment didn't predict betrayal. But they played along, because they had to survive, and some started to blur the line, even in their own minds. When you spend every day telling others that Venus means love, or Saturn means death, a part of you starts to wonder, maybe it's true. And for many centuries, nobody made a real distinction, even in the most respected libraries. Astronomy texts sat right next to astrology charts. In ancient Babylon, priests watched the stars to tell the future. In Greece, scholars like Ptolemy wrote books that combined sky mapping with horoscopic rules. In India, astrology was part of medicine. In China, comets warned of the emperor's fate. This was the normal way to think. Astronomy was the how, astrology was the why. You measured the sky to unlock the secrets of fate. It wasn't until much later that people started to question the second part. But before that, astronomers were often seen as suspicious figures. They claimed to read the heavens. They told people when to marry, when to travel, when to stay home, and when their predictions failed, which often happened, they were blamed, not just laughed at, blamed. sometimes punished, sometimes worse. A wrong prediction could cost your job, or your life, or your entire reputation, because kings took it seriously, too seriously. If an astrologer said, "Today is lucky," and the king lost a battle, who was at fault? The general, the army? No, the star reader. And so, astronomers lived in fear, not of the stars, but of the people who believed in them. They had to be careful, smart, and diplomatic, say just enough to stay employed, not enough to make enemies. Some were good at this game. They rose in the courts, became advisors, got funding for observatories, built instruments, all on the back of astrology. Others weren't so lucky. They tried to speak the truth, that stars don't decide fate, that horoscopes are made up, that science and superstition are not the same. But the world wasn't ready for that. So those voices were silenced, or ignored, or punished. The pressure to perform astrology, to deliver mystical answers, was enormous. You couldn't just say, "I don't know," or "There's no evidence." You had to say something. You had to give the people what they wanted, and that slowly corrupted the field. Astronomers stopped focusing on observation. They focused on prediction, not prediction of eclipses or planetary motion, but prediction of human behavior. That was what brought power, money, access. The stars, which once inspired wonder, became tools of politics, and the astronomers, they became court entertainers, not always by choice, but out of necessity. Still, in the quiet moments after the horoscopes were written, after the nobles were satisfied, many astronomers went back to the real work, measuring distances, studying retrograde motion, wondering what stars were made of, asking questions no horoscope could answer, and slowly, painfully, the truth started to emerge through the lies, through the fluff, through the fog of predictions, came better instruments, better math, better theories. But the stigma lingered. Even as astronomy evolved, many people still thought of it as mystical nonsense, a field for dreamers and fakers, not real scientists, and for centuries, that reputation stuck. You could spend your life charting the stars and still be called a fraud. You could write a brilliant book on planetary orbits, and people would still ask, "So what does that mean for my love life?" Some astronomers gave up trying to explain. They just kept working, kept observing, kept building, knowing that one day, maybe, people would see the difference. That astronomy wasn't about fate, it was about facts. That it wasn't about telling fortunes, it was about understanding the universe. But until then, the two paths, science and superstition, continued to twist together, sometimes peacefully, sometimes in conflict, and even today, that shadow still lingers. Ask someone about Mercury in retrograde, and they'll probably know what you mean, even if they've never looked through a telescope, because the line was blurred for so long. Some of the blur never fully went away, and it all started in those ancient courts, where a tired astronomer sat down with a ruler, a pen, and a long list of nobles wanting to know what the stars said about them. In the ancient world, being an astronomer wasn't just a job. It was a risk, a risky career, a risky passion, a risky pursuit of truth in a world that didn't always want it. And worst of all, it was a career where a tiny mistake could ruin everything. One number off, one star chart slightly wrong, one prediction that didn't come true, that could be the end of your reputation, the end of your credibility. In some places, even the end of your life. Astronomy, like all sciences back then, wasn't seen as neutral. It was deeply tied to religion, politics, and power. So when you got something wrong, it wasn't just seen as human error. It was seen as a threat to beliefs, a threat to rulers, a threat to the cosmic order, and the punishment for that threat. It varied. Sometimes it was mockery, other times banishment, in extreme cases, execution. Let's break it down. Imagine being asked to predict an eclipse. You do your math, you study your tables, you watch the sky night after night, and then you tell the king, there will be an eclipse on the 12th. But the eclipse doesn't come, or it comes a day later, or it's not visible from his palace window. Now the king is angry, and not just at the mistake. He starts asking, did you lie? Are the gods displeased? Did you just try to make me look foolish? And suddenly, you're not a scholar. You're a suspect. Because the belief wasn't just that astronomers observed the heavens. People thought they had control over the knowledge of it, and therefore control over fate. So a wrong chart. That was almost like blasphemy in some empires. The positions of stars were tied directly to religion. They were considered messages from gods, proof of divine order. So if your chart didn't match what the priests believed, you were now challenging the gods, and challenging the gods was dangerous. Business. Take the case of early Islamic astronomers. Many were brilliant. They used advanced math, built observatories, and created detailed sky maps. But they also had to constantly work around religious doctrine. They couldn't just say, the earth moves. They had to carefully phrase it, wrap it in layers of logic. Sometimes they had to publish anonymously, because if their findings contradicted scripture, or even just seemed to, they could be arrested, their work destroyed, their names erased. And it wasn't just the Islamic world. The same happened in Europe. During the medieval period, the Catholic Church controlled most knowledge. What they said about the cosmos was final. So when people, like Copernicus or Galileo, proposed something different, they weren't just challenging science. They were challenging power. Galileo, for example, used a telescope to prove that Jupiter had moons, that Venus had phases, that not everything revolved around the Earth. And what did he get for that? A trial, a forced confession, a sentence of house arrest for the rest of his life. All because he said, hey, maybe the Earth isn't the center of everything. That's the kind of danger astronomers faced. And it wasn't always about religion. Sometimes it was just about status. If you made a mistake in your calculations, you might be called a fraud or a fool. Other astronomers would discredit you. Your books would go unread. Your name would be left out of history, because in the world of early astronomy, reputation was everything. You couldn't prove your discoveries with photographs. You didn't have digital logs or automatic telescopes. Everything depended on how accurate your observations seemed to others. So even a small misstepper, missed planet, a wrong date, a cloudy night could make people doubt all your work. That kind of pressure was constant, and it made some astronomers extremely cautious. They double-checked everything, triple-checked. Some refused to publish their findings. They kept them secret, hoping one day the world would be ready. Others took the opposite route. They exaggerated, faked data, made wild claims to gain favor or funding, because the risk of being right too soon was just as bad as being wrong. You could discover something amazing, but if it didn't match the accepted model, you'd be punished, not praised. Even Tycho Brahe, A legendary astronomer with royal funding and a custom-built observatory had to be careful. He had ideas that clashed with both Ptolemaic and Copernican systems, so he invented his own hybrid model just to avoid stepping on too many toes. It wasn't until much later, centuries later, that astronomy became safer, that it became science instead of sorcery. Today, if an astronomer gets something wrong, they publish a correction. They improve their model. They move on. But back then, it wasn't that simple. The stakes were higher. Your life's work could be destroyed, your scrolls burned, your name erased, your body imprisoned. Or worse, even something as simple as saying, "The stars don't control fate," could land you in serious trouble, because saying that meant challenging kings, priests, teachers, traditions. So astronomers walked a narrow path, balancing their love for truth with their fear of consequences. And they didn't always win. Some were killed for ideas we now teach in schools. Some were ignored until long after their deaths. Others never got to finish their work, but they kept going. They kept calculating, watching, wondering. They knew the cost. They paid it anyway. Because for them, the sky wasn't just a ceiling. It was a question. And even if the answer came with punishment, they still wanted to know. For most of human history, people believed they had a full view of the sky. They looked up, drew what they saw, and called it complete. But they were only seeing half the story. For early European astronomers, the sky was like a giant dome above their heads, a fixed, eternal pattern of stars. They charted the constellations. They could see. They mapped planets and paths, named patterns, and created models. But there was one major problem. They had never seen the southern half of the sky, everything south of the equator. A mystery, not just unknown, invisible. Their entire idea of the universe was built on partial information. They didn't even realize how much was missing. You see, the Earth's curvature hides part of the sky, depending on where you stand. From Europe, only the northern constellations are visible year-round. Even at the equator, parts of the southern sky dip below the horizon. So for early European observers, star charts were based on just what they could see from their limited position. Imagine trying to draw a map of the world, but never leaving your hometown. That's what ancient star maps were like. Beautiful, detailed, but only showing half the reality. And it wasn't just about constellations. These gaps affected everything: navigation, calendars, predictions, even their understanding of space. When sailors from Portugal and Spain began traveling further south in the 15th century, they saw things that didn't appear in any books. New stars, new clusters, entire constellations that no one in Europe had ever recorded. They looked up at a sky that felt alien. The Southern Cross, for example, one of the most recognizable features in the Southern Hemisphere, was completely unknown to ancient Greeks, Romans, or medieval scholars. It wasn't on any charts. It had no myths, no stories. It just didn't exist in the minds of European astronomers. But of course, it had always been there. Indigenous people in South America, Africa, Australia, and Polynesia had known these stars for centuries. They used them for travel, seasons, stories, and ceremonies. But their knowledge wasn't part of the European scientific world. It was ignored or dismissed. So when European explorers encountered these southern stars, it caused confusion. Suddenly, the sky wasn't what they thought. It was bigger, messier, more complicated. They had to redraw their celestial maps, sometimes literally at sea. But even then, Mapping was difficult. Ships rocked, clouds rolled in, tools were clumsy, and many explorers weren't trained in astronomy. They relied on whatever instruments they had: quadrants, astrolabes, crude telescopes, and hoped for clear skies. Mistakes were common. Coordinates were off. Charts were inconsistent, and still, they pressed on. Astronomers back in Europe began to hear of these strange new stars. Some believed the sailors. Others thought it was nonsense. Why? Because their models didn't allow for it. In the Ptolemaic system, the stars were on a fixed sphere. They didn't move. They didn't change. There couldn't just be more stars. That idea broke everything, so the new discoveries were sometimes rejected. Not because they were wrong, but because they didn't fit. This made progress painfully slow. The celestial map was stuck in an old shape. Gaps stayed gaps. Errors went uncorrected for decades. And those gaps weren't harmless. For sailors, a wrong star chart could mean a wrong course, and a ship lost at sea. For calendar makers, missing stars meant wrong dates. Harvests came, too early or too late. For theorists, incomplete data led to flawed ideas about the shape of the universe. If your picture of the sky is broken, your theories about how it works will be broken too. It's like trying to solve a puzzle with half the pieces missing. You can guess. You can force things to fit, but the picture will always be wrong. And that was the world of early astronomy. Constellations like Canopus, Acherna, and Alpha Centauri, now known to be some of the brightest in the sky, were invisible to the thinkers. Of Europe, they didn't know these stars existed. And that ignorance shaped everything they believed. Eventually, things began to change. With the rise of global sea travel, more and more observers reached the southern hemisphere. They brought back logs and drawings, sketches of stars that had no names, descriptions of skies that broke the old charts. In the late 1500s and early 1600s, astronomers like Petrus, Plancius, and Johann Bayer began updating star maps. They added southern constellations. They corrected errors. They started building a more complete picture, but it wasn't easy. Every new observation raised questions. Why do some stars move differently? Why are some brighter than expected? Why are some regions of the sky empty while others are dense? The universe, it turned out, was more chaotic than the ancients had hoped. It didn't follow perfect symmetry. It didn't revolve around Earth. It didn't always make sense. And that was hard to accept. For centuries, the sky had been a symbol of order, a cosmic clock, a divine calendar. But now it was starting to look more like a mystery. The more astronomers filled in the missing parts, the more they realized how little they actually knew. This was humbling and frustrating, because every new discovery forced them to unlearn something old, to throw away models they'd trusted for generations, to admit that they were wrong. And that's never easy, but it was necessary. Without the southern sky, the celestial map was a lie, a pretty one, but still a lie. And so astronomers began the long, slow task of rebuilding the sky from scratch. Star by star, chart by chart, observation by observation. The tools improved. Telescopes got better, math got sharper, and slowly the gaps began to close. Eventually, the celestial sphere was no longer a half-truth. It became a full map, a shared canvas between north and south, east and west. But the road there had been difficult. It took centuries, and countless lives, and endless mistakes. Because in science, especially in astronomy, discovery isn't fast. It's not clean. It's messy, tiring, and often thankless. especially when the stars you're trying to find aren't even in the sky above you. In our world today, a scientific discovery can spread in seconds. A photo from a new telescope gets posted online. A theory gets shared on social media. A mistake is corrected with a single click. But thousands of years ago, none of that existed. There was no internet, no international conferences, no shared databases or research networks. Knowledge real, tested, careful knowledge moved like molasses. Breakthroughs came slowly, sometimes painfully so. Astronomers in the ancient world didn't start from scratch, but what they had was often second-hand. They relied on old scrolls, dusty manuscripts, or oral traditions. Many of their ideas came from ancient Greece, India, Babylon, and Persia. The problem was, those ideas were often written in dead languages, and by the time they were read again, they were already centuries out of date. You couldn't just fact-check a theory. There were no satellites, no photography, no reliable maps. Even basic testing tools were hard to find or didn't exist at all. If you were an astronomer in, say, 1100 CE, and you had a new idea, there was no lab where you could test it, no colleagues you could email, no telescope to help you double-check your theory. You were alone, your tools were simple, and the stars didn't give up their secrets easily. Imagine trying to confirm the shape of Earth, or the path of a planet, with only your eyes and a few handmade devices. A stick in the ground to track shadows, a water clock to mark the hours, an armillary sphere that only sort of worked. It was like trying to solve a puzzle in the dark, with half the pieces missing. To make things even harder, there was no collaboration, at least not in the way we think of it now. Today, scientists publish research that can be read instantly around the world. But back then, if a scholar in India developed a brilliant new model of the sky, a scholar in Baghdad might never hear of it. The work could remain local for decades, even centuries. Travel was hard. Language barriers were massive. Political tensions blocked the flow of ideas, and books, when they existed, were copied by hand. A single mistake by a scribe could turn an accurate equation into a useless mess. This meant knowledge didn't just move slowly, it also changed, sometimes corrupted as it moved. Theory written in Greek could be misunderstood when translated into Arabic. Then again, when translated into Latin, by the time it reached a European scholar in the 1400s, it might barely resemble the original. And still, this was considered progress. Astronomers were building ideas on top of older ideas, layer by layer. They looked to the past because that's all they had. Aristotle, Ptolemy, Aryabhata, Albertani, these ancient names carried authority. If a theory had survived for 300 years, people assumed it must be right. But often, it wasn't. For example, Ptolemy's geocentric model, the idea that Earth sat still at the center of the universe, dominated science for over 1,000 years. It was beautiful, elegant, and almost completely wrong. Still, scholars clung to it, trying to make the math work. They added circles on top of circles, epicycles, to explain planetary motion. They bent logic to fit what they thought was true, and why wouldn't they? They didn't have a better system. They didn't have the tools to test alternatives. It wasn't. The people didn't want to find the truth. They simply didn't have the means. And so theories lingered. Wrong ones lasted for lifetimes. Right ones took forever to be noticed. Even when someone had a new idea, they had to be cautious. Bold theories could get you laughed at, or ignored, or, in some cases, punished. So scholars often buried their most radical thoughts deep inside long, dense books. They would present ideas as possibilities, never certainties. They would write in riddles or indirect phrases, trying not to offend powerful leaders or institutions. This slowed everything down. Progress wasn't a straight line, it was more like a stuttering crawl. One scholar would suggest something. 50 years later, someone else would test it. Then maybe, after another century, it might show up in a widely read manuscript. Sometimes, a great discovery was lost, entirely buried in a forgotten library or destroyed in a fire. So much knowledge simply disappeared. Wars, floods, neglect, politics, all of them took their toll on ancient science. For example, when the Library of Alexandria burned, countless astronomical texts were destroyed. Writings that might have sped up human understanding by centuries gone in a single event. Other times, books survived but were never read. They sat on dusty shelves, ignored by the next generation. Either the language had changed, or the ideas were too unfamiliar. This was the tragic rhythm of early astronomy. A discovery, a delay, a rediscovery, another delay. Even simple things, like tracking a comet, required years of observations. There were no long-term databases, no global networks sharing updates. So if a bright object suddenly appeared in the sky, people in different places would record it. But their notes might never be compared. They might call it by different names. They might misunderstand what they were seeing. One culture might think it was a god. Another might call it a bad omen. Few would know it was the same object. It could take generations to piece together those scattered clues. Still, progress did happen. Just slowly. The invention of better tools helped, though that too took time. Even the telescope, once invented, wasn't adopted overnight. For years, many scholars refused to use it. They didn't trust it. They didn't understand what they were seeing. They thought their eyes were better. It took decades for telescopes to become accepted, and even longer for them to become standard. In the meantime, astronomers kept watching the sky with their eyes, drawing with their hands, calculating with fingers and rudimentary math. Every discovery was a grind. Every new star, every corrected orbit, every accurate eclipse prediction, hard-won through patience and repetition. And the breakthroughs, when they came, felt like whispers in the dark. Rare, quiet, easily missed. But they built on each other. One scholar's corrected calendar helped another's lunar chart. A precise measurement of the solstice improved future sundials. A better way to measure angles led to cleaner star maps. Slowly, painfully, and beautifully, astronomy grew. Each century added a few more facts. Each generation improved on the last. It took thousands of years to get from guessing at the stars to understanding what they are. Because back then, a breakthrough wasn't a sudden leap. It was a quiet accumulation of notes, of drawings, of whispered ideas that finally found their place, and all of it, every little step, was done with almost no help. No modern tech, no fast feedback, no easy testing, just long nights, old books, and the deep desire to understand the sky. The early 1600s were tense. Not in the way wars are tense, not in the way revolutions are loud, but in a quiet, slow-burning way, the kind only astronomers truly felt. Because something was coming. They didn't know it, but they could feel the weight of the questions pressing harder than ever. The stars were still distant, still fuzzy, still full of mystery, but there were whispers, rumors of a new tool, a strange glass tube, a device that could change everything. Astronomers didn't yet call it a telescope. In fact, many had never even seen one. But something was in the air. Clarity, finally, was just barely within reach. For centuries, the greatest minds had done all their work with nothing but their eyes. Their instruments, armillary spheres, sextants, quadrants, were clever but primitive. Their charts were filled with careful guesses and long-term observations, and their theories were often tangled in ancient assumptions. But by the early 1600s, those minds were ready. They had mapped the heavens the best they could. They had drawn patterns in the sky by watching stars for years, even decades, and they were running into a wall. Every astronomer knew it. You could only stare so long with your bare eyes. You could only squint so hard before mistakes crept in. No matter how skilled you were, the tools available simply weren't enough. Something better had to come, and soon. The frustration was deep. Scholars had been making incredibly precise predictions with incredible effort. Eclipses were timed using water clocks and dusty old math. Planetary orbits were traced using strings and sticks, and errors, even tiny ones, made entire models fall apart. You could spend 10 years tracking Mars, and still end up off by just a fraction of a degree, and that tiny mistake, it could ruin your career. Or worse. Yet even with this pressure, they kept going. They observed, they recorded, they hoped. Then, a whisper. A man in the Netherlands had built a tube that made distant objects appear close. It wasn't made for stars, not yet. It was a curiosity, a toy almost. But the idea spread like wildfire. Suddenly, astronomers perked up. Could this be the answer? Could a device finally bring the moon into focus? Could the strange movement of Jupiter finally make sense? Some began experimenting right away, but good lenses were hard to make. Glassmakers weren't used to this kind of precision. Most lenses were cloudy, warped, or full of bubbles, and so even the earliest telescope-like tools still disappointed. Still, something had shifted. For the first time in history, astronomers began to believe that they might actually see the truth, not just guess it. They wouldn't have to imagine craters on the moon. They could look. They wouldn't have to theorize what Saturn was made of. They might soon observe it with detail. The pressure and the excitement were unbearable for some. And tragically, not everyone would live to see what came next. Many brilliant minds, names now buried in old texts, worked themselves to exhaustion in the years just before the telescope changed everything. They mapped the skies with intense care. They corrected ancient errors. They pushed boundaries of knowledge, knowing that something had to give, but they never saw the breakthrough. It's a bittersweet part of scientific history. Imagine dedicating your life to a question and passing away just before someone else finds the tool to answer it. Johannes Kepler, for example, came so close. He lived to hear of Galileo's telescopic discoveries, but he never used one himself for serious astronomy. Instead, he built his groundbreaking laws of planetary motion the old-fashioned way, with numbers, sweat, and the night sky. Tycho Brahe died just a few years before the telescope exploded onto the scene. He left behind detailed records, some of the best naked-eye observations ever made. But he never saw Saturn's rings. He never glimpsed the moons of Jupiter. He never saw what his data would unlock when paired with a new instrument. This was the great divide. The early 1600s were like standing on a cliff's edge. On one side, ancient techniques, ancient tools, endless patience. On the other, a modern scientific revolution waiting to burst. And the people living in that moment, they felt both the fatigue of the old world and the spark of something new. For centuries, astronomers had used star charts filled with error margins. They accounted for poor visibility, clouded nights, and human limits. Now, the idea that glass could change that clarity could be engineered, felt like magic. But it wasn't magic. It was math, it was optics, it was science, and that realization that tools could be as powerful as thought reshaped how astronomers saw their own work. They began preparing. Books began to shift their tone. Diagrams became more detailed. Theories leaned harder on observation than tradition. Still, nothing happened overnight. Even after Galileo turned his telescope to the stars, many people didn't believe what he saw. Some scholars refused to look through the lens. They thought it was trickery, or worse, heresy, so the telescope was slow to be accepted. But in this chapter, the moment just before it all began, the groundwork had been laid. Astronomers in the early 1600s were already thinking differently. They were more daring, more willing to challenge old beliefs, and more ready than ever to abandon models that didn't work. Even without seeing Jupiter's moons, they suspected there was more to learn. Even without zooming in on the lunar surface, they guessed it wasn't perfect. They sensed that the universe was more complex than anyone had imagined. And most importantly, they were no longer afraid to admit what they didn't know. For centuries, admitting ignorance had been dangerous. It could ruin your reputation. It could make kings doubt your predictions. It could get you branded as foolish or worse. But in the early 1600s, astronomers began to embrace the unknown. They began to ask questions without fear. Why do planets move the way they do? Why does the moon seem to change? Why are the stars fixed, or are they? These weren't just technical puzzles. There were signs of a bigger shift, a hunger for clarity, for truth, for proof, and the telescope was just the beginning. Soon, a simple glass tube would show mountains on the moon. It would reveal that Jupiter had its own moons. It would prove that Saturn wasn't a perfect sphere. It would shake the foundations of belief, science, and society. But right before that, in this moment, this strange, beautiful pause, astronomers were still reaching out with bare hands, still charting the sky by instinct, memory, and willpower. They were on the edge of history, exhausted but ready, imperfect but daring, blind but looking, and just beyond their reach was the lens that would change everything. They stared at the sky for years, not through lenses or screens, but with tired, burning eyes, through cold nights and endless calculations. They made mistakes, they faced pressure, they walked alonely, rode, some were mocked, some were punished, some died, never knowing how close they came to the truth, and yet they kept going, with no real instruments, no certainty, no comfort. All they had was a question. What's up there? So tonight, when you glance at the stars, and you see them sharp and clear through apps, telescopes, or even satellite photos, remember those who couldn't. Imagine looking up, and knowing you'll never truly see them, never truly understand, but still trying, still hoping. Sleep easy tonight. Someone else suffered so you could understand the sky. Thanks for watching. If you felt even a moment of wonder, give this video a like. And if you're curious about the forgotten struggles of the past, subscribe to Restless Historian. There's more history to lose sleep over. See you in the next chapter.